Hello, welcome back to your subject CMT, Construction Materials and Testing. Okay, so this is your Module 2. We will talk about aggregates. In your Module 1, previous Module 1, we talked about the material properties, okay, or properties of material that are important to be considered if you are going to use that type of material on construction. Okay, so we discussed on physical, mechanical, and chemical properties. Okay, so let's try now to focus on the aggregate. Okay, so this is a material to be used on construction. We call this one aggregates. Okay, so we have a lot of definition. Okay, so the term aggregates generally refers to mineral particles which have rock as their origin. Okay, unless otherwise specified. So that is the common definition for an aggregate. It is in the form of rock, or it is coming from a rock. Okay, we can describe also aggregate. Or actually, this is the use of aggregate. Okay, that is an inner filler material, such as sand and gravel. Okay, to be used in making concrete. If you say concrete, okay, it is a mixture of a cement and then of course an aggregates. So again, aggregates is just additional to a cement for us to have a concrete mix. Okay, we will be discussing the importance of that aggregate on a concrete mix. And then aggregate make up to 60 to 75% if we are talking about here of a normal or ordinary concrete. Okay, or if we are talking here of an asphalt or pavement, or that is actually a bituminous concrete. Okay, that is composed of 90% aggregates. Okay, what is the difference of this ordinary concrete and then bituminous concrete? Is that ordinary concrete is using what we call as the Portland cement. Okay, that is what we know as the cement. Okay, commonly known as the cement. And then we have what we call as the bituminous concrete, wherein our binding agent, okay, instead of that cement or that Portland cement, we will now be using asphalt. Okay, asphalt as our binding agent for the concrete mix. So that is just the commonly used type of concrete mix. For ordinary or Portland cement concrete, that is 60 to 75, okay, composing of aggregates. But for bituminous, that is almost 90% of the mixture. Okay, so it could be aggregate, could be sand, gravel, boulders, stones, or rock that can be crushed into particles. Okay, so byproduct, or it could be a byproduct or waste material from industrial process or mining operation, as long as it is in the form of rock. Okay, you know, of course, the physical property of rock that we need, of course, for construction. And then these are the aggregate sources. So this is the natural aggregate. We call this one natural aggregate. Those that are coming from sand and gravel mine, or that is sand and gravel pit. Okay, aggregates that came from unconsolidated sand and gravel deposits, typically deposited by streams, or we call that one the alluvium or glaciers. This is just, of course, we are just talking here of the sand and gravel that is coming from the riverbeds, streams, and so on and so forth. Okay, those are on its natural shape. And then of course, other source of natural aggregate is quarry. Okay, aggregates that came from bedrock deposits. Bedrock, which is consolidated rock, includes granite, basalt, and so on and so forth. Those are just types of rocks. Okay, so it's either a natural aggregate, it's either coming from a riverbed, or that is to be quarried. Okay, quarry from a quarry, just like an open pit mining. But we are referring here to the aggregates. Okay, contrived aggregate. So what is a contrived aggregate? That could be a recycled. Okay, products that include crushed concrete, bituminous, or demolition debris. In some instance, taconite tailings. Okay, so if you say recycled, okay, recycled aggregates, this is, for example, we have here an old concrete and you are going to crush that one. That could serve as an aggregate. That is considered as an aggregate. Okay, you are going to crush an old concrete or an old bituminous concrete or asphalt pavement that we are talking about. Okay, that could be considered as recycled aggregate. Okay, so these are the methods of extraction, okay, and processing. So first is underwater sources. Okay, so dragline excavation, dredging. Okay, so as you can see, we are getting those aggregates inside or underwater. okay, from a body of water. And then, of course, land sources, truck drills, blasting bedrocks, crushers, and screens. Okay, so the common here on our place is this, of course, underwater sources. You're getting it, of course, from the riverbeds, and then, of course, the blasting bedrock. Okay, you are going to blast a very big rock, and then you're going to parting this one into small pieces. Or we can, if you need a finer aggregates, okay, just like sand, you want to make a sand out from a rock, then we have the process what we call as the crushers. Okay, so we have what we call as the crushing plant. They are going to crush the big rocks into smaller aggregates, into a sand, and of course into a bigger size of aggregates. Okay, so these are the methods of extracting and processing. Now we have this classification of aggregates. Okay, so there are a lot of classifications. First is based on shape. Okay, we can classify aggregates based on shape. Okay, we have here what we call as the rounded aggregates. Okay, that is of course on the shape itself, rounded. Irregular or partly rounded. Okay, that will just be almost a flat, but the size is a round. Okay, rounded shape. And then angular aggregates, those aggregates that has an angular sides or edges. And then flaky aggregates, elongated aggregates, flaky and elongated aggregates. Okay, so those are the types. So as you can see, these are your rounded aggregates. Okay, rounded aggregates. Okay, you can read this one completely. Okay, so the rounded aggregates are completely shaped by attrition and available in the form of seashore gravel. Rounded aggregates result to the minimum percentage of void, 32 to 33, hence gives more workability. Okay, if we are talking about here of voids, okay, if we are talking here of voids, we are talking here of the spaces if you are going to put a pile of these rounded aggregates. So the spaces in between these aggregates, that is the void that we are talking about, or the spaces. If you are using this rounded aggregate, your voids or your spaces is around 32 to 33% of course, the volume. Then, if that is the case, then that makes the mixture workable. If we say workable, it is easy for us to be mixing and then, of course, to be pouring. Okay, so that is the advantage of a rounded aggregate. So this require lesser amount of water cement ratio. Okay, because if we say water to cement ratio, the mixture of the concrete, okay, the amount of water we are going to add on the mixture, that is the water cement ratio. Okay, so if you are using a rounded aggregate, since that is workable, the mixture is workable due to rounded shape of that aggregate, it is easy for us to mix that one. You do not need to add a lot of water for you to mix the concrete mixture. Okay, so that is the meaning of that. So that is the advantage of your rounded concrete. However, they are not considered for high strength concrete because of poor interlocking behavior and weak band strength. Okay, so what does that mean? Why is it? It is good because we can mix easier because of its shape rounded. However, if we are talking here of the strength of the concrete that we are going to make, that will not be what we call this one, that is not suggestible because of its effect on the strength, which is actually not that high. Okay, the strength will not be that high if you are using a rounded aggregate. Okay, why? Because as explained by this sentence, that poor interlocking behavior, or there is a weak band because of the shape circle. There's a weak band between the aggregate and the cement paste. Okay, it is rounded, so it is easy for that to be separated. So that is rounded aggregate. And then we have here irregular aggregates. So as you can see, there are examples on the pictures. Irregular or partly rounded aggregates are partly shaped by attrition, and these are available in the form of spit sands and gravel. Irregular aggregates may result 35 to 37 of the voids. In here, on a rounded aggregate, that is just 32 to 33. But for irregular or partly rounded, okay, it is not purely rounded shape aggregates, there will be a bigger amount of void or space. and this will give lesser workable. So again, because it is not perfect, not all around the aggregates, it will make it a little bit harder for us to mix this one. If you tried mixing a concrete mix, you can actually say something about this. Okay, this explanation here. Again, if you tried mixing a rounded aggregate, or if you tried mixing flat or angular aggregates, you can tell the difference. Okay, so that is the good thing supposedly if we are on face-to-face class, because your CMT laboratory will be, of course, hands-on. However, we cannot do that since we are online. So in your CMT, you will just be, of course, depends on our setup. If I am going to do the activity and you are going to what to call this one, you are going to watch and learn from what you are going to view, or of course you are going to watch other videos. So that is the flow of our CMT lab, and you are going to, of course, compile or make a report out from what, of course, you observe. However, again, just like what I'm saying, if this is supposedly a face-to-face class, then it is a good thing because you are the one to do the activity itself yourself. Okay, so that's it. So irregular aggregates. So again, this rounded will give us low strength, but since in your irregular there are those with flat, with angle, so this is just like a little bit of mixture. It is not purely round, so it will be considered a little bit higher strength than this rounded. Okay. However, it is a little bit harder for us to mix, so less workability. If that is rounded, more, or that is workable, but in here, okay, partly rounded, it is less workable, but of course the effect on the strength is better. Okay, angular aggregates. So actually this is arranged. Okay, angular aggregates. So there will be no rounded. It is already angular. The edges are already angular. The corners are angular of these aggregates. So that will give us a better strength. However, again, it will be more difficult for us to mix. So it will be a little bit workable, or less workable. And as you can see, the voids will become higher and higher. Okay, so that's it. And we have elongated aggregates and flaky aggregates. That is, of course, just on the shape now, or on the physical property of the sand itself. If that is elongated, then that will belong to elongated aggregates. If it is flaky aggregates, then that is almost a little bit flat, but there will be an edge. Okay, so those are just the types, but commonly we can just segregate this one into a rounded and angular. So if we say rounded aggregates, these are actually most coming from the natural aggregates, or that is just coming from the quarry. So all you need to do is screen this one, or segregates the sizes, or from the riverbeds. All you need to do is get that one, and then again screen and separate the sizes. However, these angular aggregates, these flaky, elongated, okay, these are most coming from the this one on top, crusher plants, or blasting bedrocks. Okay, from crushing, if you're going to crush that one, you will not expect that the shape of the result aggregate is rounded. Okay, it will be angular. It could be flaky, elongated, but it will be sure angular. Okay, angular, I mean. Classification of aggregates. Okay, so that is the classification based on shape. This is now the classification based on sizes. Okay, so we have what we call as the fine aggregates. Okay, so and what we call as the coarse aggregate. So there is the specific use of this fine and coarse aggregate on the concrete mix. Okay, so if you say fine aggregate, okay, fine aggregate. Okay, by the way, if you will read this one, aggregates are available in nature in different sizes. Okay, the size of aggregate used may be related in the mixed proportion. Okay, type of work. So if you say type of work, it depends. If you want to finish the side of a wall, since let's say that is very rough, you want to finish that one smoothly, of course what you need there is fine aggregate, or what we know as the sand. You cannot use their coarse aggregate. If you say fine, by the way, these are the small sizes, or the fine, coarse fine, literally fine. Coarse, that is the big sizes. Okay, we will try to discuss about the sizes later on. So let's say your work is to finish, to make the rough side of a wall smooth, then what you need is a fine aggregate. Okay, so it depends on the type of work. So fine aggregates, okay, sand or crushed stone in a size less than 5 mm, or that is if in inches 0.2 inch. Okay, so that is the size of your fine aggregates, less than 5 mm or 0.2 inch. Okay, fine aggregate content usually is 35 to 45% by mass or volume of the total aggregates. If you are trying to create a concrete mix, there is of course the cement, okay, the cement, Portland cement, or it could be an asphalt if you are on bituminous concrete. And then of course you need the the fine aggregate, the sand. Okay, we commonly know that one as the sand. And then of course you need the coarse aggregate. Okay, the bigger sizes. Not just only fine, not just only coarse. You need the mixture of this. The reason is that, of course, let's say you want to create a concrete mix. Okay, first you put there a gravel or the big sizes, the coarse aggregate. However, if you are going to mix that one, there will be a lot of void. So you need smaller pieces to fill this void. So now you will be using sand. However, sand again is not that fine. Okay, it's not that fine. There will be a very, very small. Yes, the void of the coarse aggregate will be filled by sand. But there will be a small, very, very small void of those sand also. So that is now the use of your cement paste. Okay, that will now penetrate the small voids and then fill that one. So that, of course, you will have a solid concrete. Okay, so again, that is that the mixture there is composed of 35 to 45% of purely fine aggregates. Okay, we are talking here of the aggregate only. And then we have here again of course the coarse aggregate, that is the bigger sizes. This could be again a gravel or crushed stone. Okay, so again you have here a rounded, or this is a crushed stone. Okay, so if this is smaller than 5 mm or 0.2 inches, that coarse aggregate will be a 5 mm and above, or bigger than 5 mm, or that is 0.2 and above, equal to 5 mm and above. And then typically that is 9.5 and 37.5 mm in size. Okay, the division of the size of this fine and coarse is the 5 mm. Less than 5 mm is fine. Bigger 5 mm, 5 mm and above is coarse. However, there are these specific sizes. Okay, based on experiment, there are these specific sizes that are that will yield a better result when it comes to the concrete mix. So typically, the good size for a coarse aggregate is between that 9.5 to 37.5 mm. Okay, but still that 5 mm to that 9.5 is considered as coarse aggregate. But again, typically the size that will give us a good result on the concrete mix is that 9.5 to 37.5, or in inches that is 3/8 to 1.5 inches. Okay, so that is coarse aggregate. Okay, so rock and mineral constituents in aggregates. So what are these types, or actually where are these aggregates coming from? Minerals, it's either it is a mineral, igneous rocks, metamorphic rocks, sedimentary rocks. Okay, so these are just actually explaining where this aggregate is coming from, what type of aggregate are these. So first is mineral. These are the types of mineral that can be considered as an aggregate. Okay, silica, silicates, carbonates, sulfate, iron sulfide, iron oxide. So it depends on the type of element, but that is still just a rock, considered as a rock. So if we say silica, the example of that is quartz, opal. Okay, for silicate and so on and so forth, you can read this one. So gypsum, phytite, marcasite, and so on and so forth, magnetite. So these are just types of mineral that can be used as aggregates. Okay, so igneous rocks, of course, that is just the type of the rocks. Granite, syenite, diorite, and so on and so forth. Okay, basalt. For sedimentary rocks, by the way, if we say sedimentary rocks, that is again sediments, consolidation. The rock is made from consolidation, so that is basically or commonly found on the riverbeds. Okay, small pieces which are being consolidated because, of course, of the flow of water that is now from time to time that will be consolidated into different shapes or different sizes. So sedimentary rocks. Okay, you discussed this one in your I don't know what subject is that, but that is discussed on your minor subjects before. Okay, so these are just the examples: conglomerate, sandstone, claystone, carbonates, chert, and so on and so forth. Okay, metamorphic rocks. Okay, this is coming from a metamorphic rock. Example are marbles, amphibolite, hornfels, slate, and so on and so forth. Okay, so these are the sources of our aggregates: minerals, igneous rocks, sedimentary rocks, metamorphic rocks, based on the type of the element, of course. Okay. So, in this table, you can see here aggregate property. Is this okay? Let's try to zoom. Aggregate property: strength. Okay, these are the properties that we need. Okay, this is the physical, mechanical, and then chemical properties that we need to investigate on aggregate. Okay, so first is the strength, of course, the strength of the aggregate. Since what we are after on a concrete mix is the strength, that is our main characteristics that we need to focus on a concrete mix, the strength. So of course, if you are using that aggregate on a concrete mix, you need to know the strength. Okay, so strength. And how to test that one? These are actually the procedure or standards that we will follow in testing the strength of this aggregate. So we have here ASTM C39, or that is equivalent to ASH to T22. By the way, what is this ASTM? These are what we call this one, groups, or yes, these are groups which are established groups of testing materials. Okay, American groups. ASTM stands for American, I forgot that one, testing materials. Okay, for ASH2 is still American. We are talking here about highways. Okay, so these are just groups, different groups of different American groups about focused on establishing standards on materials and of course testing. So ASTM, different group from ASH2, but they have of course the same purposes or the same standards. I mean the same way or the same after. So okay, so this is ASTM C39 is the same as ASH2 T22. They are after the testing of strength of an aggregate. Okay, so hardness. Okay, these are the testing. Okay, so by the way, in testing the strength, we call that one the crushing strength test, because they are going to crush these aggregates, and then by means of crushing, they will now be able to, okay, this test will now be able to measure the strength. And then for hardness, okay, we discuss about these properties on the module 1. Okay, what are these? Strength, hardness, and so on and so forth. Hardness, okay, that is now the abrasion test. Okay, so that is ASTM C131, or that is AS2996, T96, and so on and so forth. So impact value, that is impact test. So this is your test, ASTM blah blah blah. Resistance against weathering, okay, that is soundness test. Shape of aggregate, that is shape test. Bitumen adhesion, okay, bitumen adhesion test. Specific gravity or relative density, that is of course specific gravity test. And then water absorption test. Okay, so in your laboratory, these are what we are going to do: testing materials, and then testing of course concrete mix or bituminous concrete mix. So that is what we are going to do. Okay, we are going to do on your laboratory. So these are our guide in testing these properties. So it's either ASTM or ASH2. HTM or H2. So these are the standards, the procedures that we are going to follow in your laboratory. Okay. So let's proceed. So this is your crushing strength test on aggregates. Aggregate crushing value gives the crushing strength of aggregate up to which it can bear the load without fail. Okay, of course, you're going to crush that one, but of course the amount of load that is applied on crushing that stone or that aggregate is measured. So whatever load it can carry before it will fail, that is the crushing strength, or that is the strength of the aggregate. Abrasion test, okay, hardness property of aggregate is determined by conducting abrasion test, Los Angeles abrasion testing machine. This is what we call for this type of machine that will test the abrasion or the hardness of the aggregate. Okay, so we have here in the picture. In this one, you are going to put, of course, the aggregate, and then you are going to crush it one. We have this what to call it, machine. I mean apparatus. Okay, so this is the machine. So this is actually rotating. You are going to put inside the aggregates, and then you are going to on that one that will, of course, rotate. Okay, so the aggregates will be applying friction with each other, so the aggregates will be losing parts of it. Okay, and of course that will be on the procedure of the test. Impact test. So this is that you are going to use this machine. Impact value of the aggregate will give aggregate capability against sudden loads. So there will be an sudden application of load on the aggregate, and that will be measured by this machine, of course. Soundness test, okay, to determine the weathering resistance of aggregate soundness, test is conducted. Okay, if the resistance against weathering is good for aggregate, then it will have high durability. So how are we going to test that one? Instead, of course, putting that one under the environment or in the environment, and then of course observe that one in a very long period of time, that's not what we're going to do. We are going to make use of chemicals, okay, to test these aggregates. So as you can see, what you have here is chemicals to test the soundness or the durability. And then shape test on the aggregates. Okay, we are going to test the shape. Okay, shape of the aggregate is also important. Consider the construction pavement. This is what I'm saying a while ago. Shape is important because shape contributes to the strength, isn't it? If that is round, again, as I've explained a while ago, rounded aggregate, it will be giving you weaker concrete mix compared to angular aggregates. However, there will be an effect of the shape also when it comes to the workability. How easy you are going to mix that one based on the shape. So we need that shape test. Okay, and then bitumen adhesion. Okay, if you say bitumen adhesion, we are talking about here about the adhesion, how it will stick to the bituminous materials. Okay, so bitumen adhesion test will give the stripping of bitumen from the aggregates. Okay, in case of bitumen pavement, the bitumen should be in pure contact with aggregate. To attain this, aggregate should be clean and dry. To determine the stripping value of the bitumen static immersion test is conducted in aggregates. So all you need to do is measure the strength of the the adhesion of that asphalt to the aggregate. So actually, it depends on the aggregate itself. Let's say that we are using the same or exactly the same type and property of bituminous cement or asphalt. Then what will just be changing is the aggregate. Then of course that will give you different results. Okay, so it will depend solely on your aggregates. Okay, so if a specific gravity test, what you need here is of course a weighing balance. Okay, you had this one before in your physics or in your chemistry. Okay, so you've done weighing materials and of course solving what is the specific gravity of that. So that's it. This is the of course bulk specific gravity. And then we have the apparent specific gravity. So if you say bulk specific gravity or simply specific gravity, that is of course the density over density of water. So how do we get the density? dry weight of the aggregate over total volume of aggregates. However, the difference of that with apparent specific gravity is that, okay, look at this, volume of aggregate without void. So if you are referring to the common specific gravity, you are using the volume of the total, including the void inside. Let's say this is the sand, or this is the gravel. You want to get the specific gravity of that, that will be based on the total volume, whatever that volume is. But if you are talking about the apparent specific gravity, the volume that you will be using is, you are going to subtract the spaces, because of course, even if that is a rock, there will be small spaces inside, or the voids. You are going to subtract that one if you are using the apparent specific gravity. Okay. What else? Water absorption. Again, this test is, of course, to measure how much water that specific type or specific class of aggregate will absorb. It is important because the water in a concrete mix should be measured. Okay, the water, that is what we call the water to cement ratio. The amount of water in the mixture should be measured. So we need to consider how much water that aggregate will absorb, because that is important. That should be considered in the calculation of the amount of water, or the water cement ratio. Okay, that is water absorption test. And then grading of aggregate. Okay, so how do you know the sizes of these aggregates? That is now your grading of aggregates. Okay, so we will be using here Sieve. Okay, I will be showing you that one on the laboratory. Wherein you have just like, it depends. If you are grading a coarse or a fine aggregate, we have Sieve for coarse aggregate. We have Sieve for fine aggregates. So for example, this is a Sieve for a coarse aggregate. There are layers of screen with sizes of openings arranged from bigger opening to smaller opening. Okay, you are going to put the coarse aggregate on top, and that will be screen. Okay, whatever remains on that screen, there will be a corresponding size for that. Same thing with the fine aggregates. But of course, you will expect that the openings will be very small. The opening of the screens will be small. Okay, so again, for fine aggregates, for grading a fine aggregate, we will be using 7 standard sieves with openings from 150 micrometer, or that is actually 0.15 mm, to 9.5 mm. Okay, again, we discussed about the sizes of fine and coarse. And for coarse aggregate, for you to grade this aggregate is, we will be using 13 sieves with opening from 1.18 mm to 100 mm, or that is in 0.046 inches to 4 inches. Okay. So this is for an example of fine aggregate grading. So for example, you have a certain amount or weight of fine aggregate. All you need to do is put that one on the highest sieve. Okay, for fine aggregate, that will of course pass, the smaller will pass going below. So there will be amount of these fine aggregates remain on each of the sieve. That is how we will know the grading. So for example, of course, it again arranged from the bigger opening to the smallest opening. So 9.5, 4.75, 2.36 mm going down, 2 point something mm. Okay, so again, we will be doing this one in your laboratory. So in here, percent passing by mass. What do we mean by that? What percent in terms of the total mass will pass in that sieve? So if you will try to read this one, 100, it means 100% will pass your 9.5. It means that if you're going to put that, when you put that one, nothing is left on that 9.5 in mm sieve. Okay, so in here 95 to 100, it means that there will be screen on 4.75 mm or nothing. So again, that is just the range of what will remain based on, of course, the limits given by the fine aggregates. So we have here coarse aggregate grading. So the same thing as your fine aggregates, only that we will be using bigger sizes or bigger opening of your sieve. So we have here now in after that one, after grading this one, we have what this important quantity or term or important value. In grading, we have what we call as the fineness modulus, okay, obtained by adding. This will actually determine which size of the fine aggregate is, which of the size has the most, which of these has the most size of the fine aggregates, or the concentration of the size of the aggregates. Is it concentrated here, or is it concentrated on the bigger sizes, or is it concentrated on the finer sizes? So that is the fineness modulus. So obtained by adding the sum of the cumulative percentage by mass of a sample aggregate retained on each of the specified series of sieves and dividing the sum by 100. So the specific sieves are, okay, again, these are the specific sieves. So we will be having here example, sieve analysis and fineness modulus of sand. Okay, by the way, fineness modulus is applicable only for fine aggregates. Okay. So in here, so again, that is arranged into this manner, the sieve, and you are going to put the sample on top, and that will be screened. So according to our data in our example, percentage of individual fraction retained. Okay, you need to consider this. You need to be very careful with this percentage. If say percentage retained, that is the percent of the aggregate that is retained on that sieve. If we say percentage passing, that is the percentage that passed. Okay, that passed through that sieve. So you need to differentiate this, retained and passing. Okay, so retained, so it means 0. Why? Because 100% of that passed your sieve 9.5 mm. Okay, so if you will try to add this retained and then passing, that should be a total of, or yes, if you are going to add, for example, in here, since you just, that is the very, very first sieve, you are going to add, that should be the total mass. And then whatever is retained there, subtract that one. If you will add this one, that will be the total. For example, here, since nothing is retained, so everything is passing, if you will add the percentage of the retained and then passing the next sieve, that should be equal to the original on top. Okay, here, look at this. 13 in your sieve 2.36. What remained is 13%. What passed is 85%. You're going to check 85 plus 13, that is the percentage that passed the sieve on top of that. Okay, so again, that is for you to check your data. And then of course, all you need to do is, if you will add this retained, that should be a total of 100. Whatever will retain, that should be a total of 100. By the way, there will be this very, very small sizes that will pass to the very, very smallest size of the sieve, that will be retained if you will try to put a pan. Of course, that is a very, very tight, or that is a closed pan, impenetrable pan. So whatever that will pass to the very smallest, that will remain on the pan. So if you will consider that, that should add to 100%. It will go to that original total of the weight if you are using weight by weight. Okay. Then how do our after here is your fineness modulus. How are we going to calculate that one? Is all you need to do is have your cumulative percentage retained. We are talking here of retained. Okay, the fineness modulus. Whatever is remaining or retained on that, not the passing. We will focus on the retained. Okay, so cumulative percentage retained by mass. If we are using mass, of course, but that is the commonly used by mass, not by volume. Okay, for cumulative, what do we mean by that? Is all you need to do is add whatever is retained on this level from the top to this level. Go to the next level, that is the cumulative. Add everything on top to that level. Go to the next, add everything on top to the level. That is the cumulative percentage. So if you want the cumulative percentage at your 1.18 mm, all you need to do is add all this from 1.18 going up. So 20 plus 13 plus 2 plus 0 will give us 35. In here, 97 Why? Because if I am going to add everything from 150 micrometer going up, that is equal to 97. Why is it that is 97? Because there is a 3% that will be passing the very smallest opening, which will be going to the pan. We call that one the silt, or it could be a clay, which is actually not an ideal component of a concrete mix. Okay, that will make the concrete mix weaker. The more that is very very small, or that's dust, we can say that is a dust or clay or a silt, the more of that on the concrete mix will make it weaker. So that is not advisable. So if we can separate that one, the better. Okay, so that is also the importance of grading. We will know how much of the original state of that fine aggregate, how much of that is silt. Because if there is a big percentage of that silt, we need to apply a measure to reduce that amount of silt, because again, that is not advisable on a concrete mix. So how are we going to do this? It's either screen, or of course the fastest way is to wash. Because if you are going to wash the aggregate, the fine or the coarse aggregate, the silt or the clay or the dust will be washed away. Okay, so that is the commonly used method to reduce this amount of silt or clay. Again, as I've explained, silt or clay is not advisable because that will make the concrete mix weaker. Okay, it is just like a soil. That is just like a soil. Is a soil advisable in a concrete mix? Of course not. As you can see on most of the construction, there is no one that ever will be using a soil in a concrete mix. Okay, only of course these bigger sizes, fine aggregates or coarse aggregates. So this is by the way, what we're after here is the fineness modulus. So again, all you need to do is add your cumulative. In here we will not consider, this is what I'm saying, we will not consider that, we will remove that one in your cumulative percentage. We will remove that silt. That will be a waste. That will be a waste already. So remove that one. And then all you need to do is add, and whatever that is, divide it by 100. Then that is the fineness modulus. Okay, I will explain the meaning of that. If I will add this one, that is 283. Divided by 100, that is your fineness modulus, 2.83. So what does that mean? Okay, you are going to count 1, 2, 3, 4, 5, 6, 7. Again, 7 standard sieves according here to the grading of aggregate. For fine aggregate, 7 standard sieves. So what does that mean? That 2.83 means that the fine aggregate is containing most of the size of in between 2 and 3. Again, if you will count 1, 2, 3. See, so most of the size of your fine aggregate belongs to 4.75 and 2.36. So in between that size, that is the focus of that is the most fine aggregates found on the original sample. Okay, 2.83. For example, you will end up here with exactly 4. What is that? 1, 2, 3, 4. So it means that most of your aggregate in this fine aggregate have a size of 1.18. That is the meaning of your fineness modulus. Okay. If that is decimal, we are talking of in between these two sizes. Okay. Calculation. This is just another example. Okay. So 4.75, 2.36, 1.18, 0.6, 0.3, 0.15. 1, 2, 3, 4, 5, 6. By the way, in this example, your 9.5 is removed. Okay. We started from 4.75. So we have here 6. We have only here 6 sieves. So we have here originally 1000 gram or 1 kilogram. You're going to put that on top of the sieve, and that will be screened. And this will be the percentage of retained. I mean, this is not the percentage, this is in grams. Okay, because of course, what you will be having is not directly the percentage. What you will be having, if you are measuring it in terms of weight, is the weight. Okay, originally you have a 100 gram. or 1 kilogram. What will retain on 4.75? Nothing. So 0 gram. What will remain in 2.35 is 100 grams. So that means if you are trying to put that one on a percentage, okay, if you are going to put that one on a percentage, that will be 100 divided by 1000. That is the percent, multiply it to 100%, that is the percentage retained. Okay. However, that is not how this example solved that one. Not by means of percentage right away, but by means of weight. So this is the weight retained on 1.18 and so on and so forth. Okay. So if you are going to add this one, if we are going to add 100, this is 250, so 350 plus 350 is 700 plus 200 plus 100. So that means that is a total of 1000, so nothing will go on the pan, or maybe whatever goes to the pan is very very small, so that could be neglected. So if you are going to add this one, this is exactly 1000 grams, the original size or weight. Now instead of getting that percentage, we will first have the cumulative. So instead of getting that individual percentage retained, we will go directly to the cumulative weight, and this cumulative weight will give us directly your cumulative percentage retained. Okay, in this example we included the passing. Okay, again, that is just self-explainable. Retain, pass. I explained that one a while ago. In this example is to solve the individual retain and then get the cumulative retain. Again, how to get the cumulative? If you want at 0.6, all you need to do is add your individual from the top to that 0.6. So 100 to 50 plus 350 is 700. Okay, and then this cumulative weight retained, divide this one by the original, okay, sample, then multiply by 100%, you will have our percentage. So again, in your 0.15 mm, what retains there from the the cumulative, okay, from the very top is 100%. Again, what I'm saying is it's either very small is the amount of silt or that dust that will go to the pan, so that could be neglected. So if I'm going to add this one, again, fineness modulus is summation of cumulative percentage retained divided by 100. Summate will give us 275 divided by 100. You will have a fineness modulus of 2.75. That means that the size, the concentration of the size is between the second and the third, which is 2.36 and 1.18. So somewhere in between that is the concentration of the fine aggregate size. Okay, so that is fineness modulus. Okay, so testing of sand quality at construction site. Okay, we need to test this quality of sand. Okay, that is important because if we are talking about sand here, that is almost like a soil. Almost the size is almost like a soil. So there are a lot of characteristics that we need to test so that we can say if that type of sand is best used for construction. So first is the organic impurity test. If we say organic impurity, that is testing if there is a biodegradable component of that sand. Because if the percentage of organic impurity is very high, that is not recommended for construction. Because if we say biodegradable, as time goes by, that material will decay. So that will make your concrete mix weaker. Okay? So organic impurity test. Silt content test. So again, this is the test that will find out, okay, that will find out how much of this fine aggregate, how much of that is a waste. If we say waste, again, those are the soil or the very small size, the silt or the dust or the clay, okay. And then particle size distribution, okay, you need to, what do you call this one, apply your grading test on the fine aggregate or on the sand, because again there is this range of sizes that is recommended by the standards. So particle size distribution, this is grading test, okay. And then bulking of sand. If you say bulking of sand, that is actually has something to do with the water content, because if you will try to go and get a sand from its origin, you do not know what is the state of that, if it is a dry, or if it is a wet, or if it is just partially wet. Okay, so we call the amount of water of that as the water content, isn't it? That is the water content. So there is that effect of water content, because if there is a water content, that will make your volume of the sand bigger. Okay, you will try to read an article about bulking of sand. We call that one bulking of sand. Comparing to a dry, let's say a dry pile of sand, if you are going to add a small amount of water in it, that will it's either bulge because of that water content. That is different, of course, to very wet or completely wet. Of course, if that is completely wet, the same. But if that is just a small only amount of water in it, a small water content, that will bulge. Okay, that is from research and from experiments. Okay, so you need to consider also your water content of the origin of the sand. So these are the testing. Okay, testing for silt content, or actually this is number 2. So this is testing. Okay, you will be actually submerging this one, and then of course most of the time some of these will float, the very small particles or the sand or silt will float, some will settle down, so it depends on the type. And then we have here the test for grading. That is what we are talking about here on particle size distribution. We'll try to analyze the distribution of the sizes. And then test for the deleterious material, that is for the organic impurities. Okay, and then testing for bulking of sand, that is for number 4. Okay, according to experiments and researches, testing for bulking of sand, this is an example of that. Okay, so this is recommended. Fine aggregates, when dry or saturated, has almost the same volume, but dampness cause increase in volume. If we say dampness, that is just, of course, just like in the morning, you have what we call as the water vapor. That is dampness. Okay, only a small amount, but not totally wet. Dampness can cause increase in volume. That is according to research and experiment. In case fine aggregate is damp at the time of proportioning the ingredients of the mortar or concrete, its quality shall be increased suitable to allow for bulkage. Okay, so again, since if that will bulk or that will increase in volume, that should be considered. Since that is the false volume, or that is not the true volume if it bulged. Okay, so that should be considered. So this is from example. Okay, the table below gives the relation between moisture content and percentage of bulking for guidance only. See, so most of the time that is 2%. The moisture content is 2%. The amount of bulking, okay, the amount of addition in volume is 15%. For 5% water content or moisture content, that will give us almost half. That is 30. That is very, very big. Okay, 30% amount of additional volume. Okay, so that is the end of our discussion for aggregates. Coarse aggregate, fine aggregates, and the types of testing that we need to apply or we need to do before we can say that that is recommended for construction. But of course, if you will try to observe on the actual construction, okay, there are those that are getting an aggregate from a company, and of course these are being controlled by the company. The testings and the properties are being controlled, of course. But if you will see in the small construction, they are not that strict, because of course the effect of each of these are not that significant on a small construction. But if you are referring to a very big construction, let's say a high rise, this should be very, very strict. Okay, on the testing of the aggregates to be used on the concrete mix. Okay, because we are the strength of each material used on a high rise is critical. Okay, it is very critical. But for a small construction, it's okay not to focus much on this, as long as, of course, this strength is satisfied. not every property. Okay, so that is for aggregates. So if you have question, you can comment below the video and we will discuss that one on the next or on the live meeting. So thank you very much for watching.